Good evening, everyone. Welcome to this evening's Core Science Hangout. We'll start in 10 minutes' time, but if you just want to grab yourselves perhaps a pen and a piece of paper if you want to make any notes down as we go through. Good evening, folks. Just to make sure that it's all working, if you can hear me okay, can you just message on the wall if you're watching through Frog and just let me know you can hear me okay and that you are on board this evening. Thank you. Evening all, 5 minutes to go till we start the Hangout. There's a few of you logged in already, which is good to see. If you think anyone might have forgotten that it starts at 6 o'clock, feel free to jog their memories for me. You might want a pen and a piece of paper to make any notes, but if not, just sit tight for 5 minutes and then we'll start. Okay, welcome to those just logging in. We'll start in just a couple of minutes. You might want to get yourselves some paper and a bit of pen if you want to make any notes. Just hang on 2 minutes and then we'll make a start. Okay, good evening. We're going to make a start. Welcome to the night before Core Science Chemistry Hangout. Hopefully you can all hear me okay. Just message me on the wall if anything goes wrong and suddenly you can't hear me. We're going to start by having a look at all the little topics that come up in C1. Hopefully this is more of a just glance at everything in the spec. Hopefully it will be the fact that you will have a good understanding of all this stuff already, but it's just a way of getting everything fresh in your head, ready, so that when you go to bed tonight, it will all be fresh in your head, ready for tomorrow morning. So what does core chemistry look like? Well, if we have a look at the general topics, you've got things about the atoms in the periodic table. A lot of that comes up in C2 as well, so you should know that quite well already. Extracting metals, we'll look at reduction, electrolysis, etc. Properties of metals, alloys, and the different metals that we use. The structure of the Earth and tectonic plates and how life formed. There's quite a big section on oils to plastics, so looking at some organic chemistry, some alkanes and alkenes. The Limestone Cycle. They're quite heavy on environmental problems, so global warming, acid rain, recycling and quarrying. And finally, oils and emulsions. We're going to start off though by just really me emphasising a really important point, which is that you must look out for the bold bits in your exam tomorrow. So use your highlighter or underline throughout your exam, because these areas in bold are really important. The number of times, for example, with a table like this, where it says tick 1 advantage and 1 disadvantage, the number of times where I've marked past papers and people have ticked several different columns rather than just one in each one. So that's really important. Look out for the marks. You should be guessing what the examiner wants for the marks, and make sure if you've got 2 marks, you've put 2 points, etc. Also, look out for where it says use the chemistry data sheet, because there's a hint that there'll be something on there that might be useful for you to answer the question. So let's start right there then at the chemistry data sheet. Don't let it just be a piece of paper that you just put to one side in the exam and never refer to. Use the key, don't guess the numbers. So use the fact that mass is the top number and proton number is the bottom number. A big clue there with proton number that it's talking about the number of protons in the atom. We'll come back to this in a minute when we use it, but obviously you've got the group numbers at the top, which are helpful as well. And expect to use that in the first couple of questions especially. But what people forget also is there's a second side to that data sheet. There is one that has the reactivity series on there for you. The reactivity series, don't forget, will help you in the extraction of metals. Everything above carbon in the reactivity series has to be extracted by electrolysis. You can do electrolysis for the things below, but because it costs a lot of energy and a lot of money, okay, we're going to want to use other methods, and we'll talk about those later. But anything below carbon, we could use something like reduction, using carbon in there to extract the oxygen away from the ore. So that might be useful for you, so don't forget that that's there. And finally, the ions. When you're writing ionic formulae, or when you're talking about electrolysis, don't forget that these are here, okay, because people only look at the periodic table side of the sheet and forget how useful this can be. Starting off then, what you can expect then as you sit in the hall tomorrow and open the first questions of your C1 exam. Well, historically, they've all been to do with atoms and atomic structure. It might not be tomorrow, but it's quite likely that that's how they'll ease you into the paper. Should be quite familiar with these right now. The number of people, though, that don't see this as a question and leave it out is unbelievable. So really take your time, go through each one, making sure you're answering each question. Use the periodic table, also your data sheet, to help you out. So this question says, show the electron structure of boron. So you'd look to boron, you'd know its proton number is 5. If it's got 5 protons, it's also got 5 electrons, and you can write those in there, remembering that the inner shell can only take up to 2, and then you have to have 3 on the outer shell. Hence, boron is in group 3, because the group number tells you how many electrons there are in the outer shell. Slightly more complex atomic structure kind of question. I've highlighted this one because it's worth 3 marks. This question says the electronic structure of a neon atom is shown is not correct. Explain what is wrong with the electron structure shown in figure 2. Now, the reason I highlight this is because it's 3 marks. I need you to really, if you get a question like this, clearly state where you're getting your 3 marks. So using your bullet points, for example, and putting enough detail in. For example, a neon atom has 10 electrons and it's a noble gas, so it should have a full outer shell. Don't just try and get away with saying it has 1 electron in its outer shell. Try and make it really clear. So as 1 point, I'd say it has 1 electron in its outer shell. But I think they're going to tighten up the mark scheme. So make sure you also say it should have 8 electrons. Another thing that's wrong with it, if you look in the center here, it's got 8 electrons. So don't just say that it's got 8 electrons in the middle, make it clear what it should have. So it has 8 electrons on the inner shell. Don't just leave it there, make it nice and clear. It should have 2 electrons. And finally, it's got a total of 9 electrons when it should have 10 electrons. So I'll just write that down here. So make use of the space that you've got, make it clear where your points are coming from, so it's going to make it nice and easy for the examiner to mark it. A couple of key questions that I'm going to come up talk about now. First of all, within the past couple of years especially, they've really introduced the fact that you need to use values to describe a graph. They'll often include that in the question saying use data from the graph, but it's amazing the number of people that ignore that. So make sure that's highlighted in your exam. When we talk describing graphs, we can describe regions like this as increasing and these points as leveling off. But if we're asked to talk about values from the graph as well, you need to tell me, for example, that the volume of gas increases up until this point, so maybe up until 110 seconds. That's using data from the graph, okay? So increasing up until 110 seconds and then leveling off. We describe this as a steeper gradient if we'd have to, and this one as a slightly shallower gradient. So 2 to 3 marks often comes from describing some sort of graph. On the right hand side here, I just want to remind you of a straight line going through the origin and that relationship being directly proportional. So if you're asked to describe a graph whereby there is a straight line that goes through the origin, for 2 marks, you need to talk about it being directly proportional. If they ask you to use values from the graph, obviously you do that as well. Really common trend has also been describing data in tables. I'd like you just to treat these a little bit like you would your ISA case studies. So here we've got concentration of copper sulfate and temperature. So look at the pattern in the data. As this is increasing, so is the temperature. However, you get to this point here and there's no further increase in temperature despite an increase in concentration. So look carefully for this kind of leveling off idea where this variable is not increasing anymore. And secondly, just like you would in a case study question in an ISA, look out for the anomaly. So this is going up in 5s apart from at this point here. So we can talk about this being anomaly. So just treat these a little bit like the case studies and you can't go wrong. Let's talk about the overall general reactions that happen in the C1 paper now. So across all of the different subjects, I've just gathered all the different types of reactions. So hopefully you can think about what an oxidation reaction is and a reduction. Well done if you said adding oxygen and removing oxygen. You may well have said oxidation is loss of electrons and reduction is gain of electrons. That is true for electrolysis. That often comes up more in C2. Often the oxidation and reduction equations in C1 are relating to adding oxygen and removing oxygen. You've got hydrogenation also, which we'll talk about later on in terms of oils, but this is reacting with hydrogen. The clue is in the name. Can you think of the specific conditions that are needed for hydrogenation? Because they need very specific conditions. Well done if you thought of a nickel catalyst and 60 degrees centigrade. And this is when we're adding hydrogen to unsaturated lipids to make them saturated, or unsaturated oils to make them saturated. We've also got hydration here, which just like you hydrate your body by drinking water, these are reactions with water. So for example, when you react ethene with water to make ethanol, that's an example of a hydration reaction. Thermal decomposition, again, you get a clue from the name, thermal, heat, decomposition, decomposing. So it's breaking down with heat. You'll recognise it's a thermal decomposition reaction because the thing that's decomposing is not reacting with anything. You've just got a straight arrow afterwards into the two products. So for example, this is an example of thermal decomposition. This is the limestone, part of the limestone cycle. Calcium carbonate, it's not reacting with anything, it's just breaking down into calcium oxide and carbon dioxide. Cracking is also an example of thermal decomposition, okay, requiring a high temperature and a catalyst because you're trying to break the bonds and break those long chain alkanes down. Polymerization, the opposite, when you've got an alkene and you want to make it into a long polymer, that requires pressure and a catalyst. And finally, combustion. Combustion, when you're burning something, if it's complete combustion, it's in the presence of enough oxygen. So for example, we'll take a hydrocarbon like methane, react that with oxygen, because when it burns, it will react with oxygen in the air to create the two products of carbon dioxide and water. If you have incomplete combustion, when there's not enough oxygen, what you get is a couple of products. You can get a toxic carbon monoxide. That can be a product. And you can also get carbon on its own, which is soot given off. Okay, so black powder, soot given off. Just like when a yellow Bunsen burner flame goes onto a beaker, and you'll find the soot around the outside of the beaker where it will go black because of incomplete combustion of the flame. So they're the general reactions. Now we're just going to go in a little brief overview of each of those topics that we started. Again, hopefully you will know the majority of this. You might just pick up a couple of things that have just reminded you, but I know you've all revised well. So this is just to get it fresh in your heads, ready for tomorrow. First of all, atoms in the periodic table. You need to know that this is the structure of a noble gas. This one's neon. When things bond together, they want to try and get that structure of a noble gas. So they'll lose electrons or gain electrons to try and get that structure of a noble gas. Again, you'll have to perhaps draw electron structures when they're giving you the shells. For example, if I was asked to draw carbon 6, we'd have 2 in the middle and 4 around the outside. Pen numbers, so protons, electrons and neutrons. Again, you take these from the periodic table. That tells you the proton number, so the number of protons. In an atom, that's the same as the number of electrons. And as a reminder, neutrons is the whole mass, take away the protons. So in this case, they would all be 6. Looking now at the formulas of ionic substances, I said at the beginning you might need to use this ion sheet to work out the formula. So the formula of magnesium oxide then, if we take the ion for magnesium, which is Mg2+, and if we have the ion for oxygen, which is O2-, because that's 2 + 2-, they just balance each other out. So you just need one atom of each. So your formula would be MgO. However, let's take sodium oxide. Sodium up here has a charge of just Na+, and oxide again O2-. If you just put those together to make NaO, there'd still be a slight negative charge because we've only got 1 plus and 2 . So we need to double this up. We need 2 of these. So we have Na2O as our formula. Okay, thank you very much for a couple of questions that have come in as well. I will get back to those shortly, but just a reminder, if you do want to write any questions, then just put them on the wall in Frog. I've put this definition here in yellow. What is a compound? Because this is a common question for 2 marks. You must have that there are 2 or more elements, and importantly for a compound, that they are chemically bonded together. Okay, moving on to the Earth topic. First of all, we need to know about the structure of the Earth. Tends to be the crust, the mantle. These tend to be grouped together and just called the core. We need to know that the crust is divided up into tectonic plates, and we'll also need to know about Wegener and his work with continental drift. So before the discovery of tectonic plates, there was Alfred Wegener. He came up with this idea of continental drift. He said that Africa and South America once were together, and that they've now since drifted apart. Those continents have drifted apart. He's got a few, if you can think of the 3 main reasons why he came up with the continental drift, the 3 little pieces of evidence that he put forward. You can have that they fit together like a jigsaw. So Africa and South America fit like a jigsaw. A lot of people say things like fit like a puzzle or fit like something else. Make sure you're describing it as a jigsaw, not just a puzzle. There's similar rocks. Well done if you got that one. And similar fossils in Africa and South America. So that was the evidence he came up with, but not a lot of people believed him at the time. They liked the idea that there was not enough evidence to believe his theory because they didn't know about tectonic plates at the time. We now know about tectonic plates. We now know that they're driven by convection currents in the mantle, and that those convection currents are caused by radioactivity in the core, and that will cause the mantle to be moving slowly around, slowly driving these tectonic plates apart. What did the early life look like then? Well, let's take a journey from the time of a lot of volcanic activity. The atmosphere was mostly carbon dioxide. They were given out by the volcanoes. Volcanoes also gave out water vapor, ammonia, and a little bit of methane as well. How were the oceans formed? If you think about these gases in the atmosphere, well, it's the water vapor here that condensed to form oceans. And see if you can remember how high levels of CO2 eventually ended up being levels which are around 0.04% today. Think of the ways that that CO2 might have gone down to really low levels today. Well, this plant's a first clue, okay? The plants, as they evolved, plants and algae, they would have taken in CO2 and given out oxygen. That oxygen then provided the opportunity for other life. that oxygen went on to form the ozone layer, which again helps support life by protecting the Earth from harmful rays. As well as that, as well as the plants taking in the carbon dioxide, there's 3 other kind of main reasons why the carbon dioxide levels went down. You could say that they were dissolved in oceans, they became locked up in sedimentary rocks, like calcium carbonate and limestone, for example. They're also locked up in fossil fuels because they became locked up in the calcium carbonate shells of marine organisms. So those few reasons caused the composition of the atmosphere to change completely to what it is today. So further to air, we know air is a mixture of around 21% oxygen, 78% nitrogen, and a few other gases like 0.0%, 0.04% carbon dioxide, and argon. Obviously, this carbon dioxide, despite being small, is still a problem because it's increasing, causing global warming. But we might want to separate this, and this is for the higher tier. You might want to separate the mixtures of gases in the atmosphere because you might want to use it. You might want to use nitrogen, for example, for the Haber process, or you might want to collect some oxygen for some reason. And what you do then is you'd cool down the air, the water vapor would be absorbed. The carbon dioxide is sometimes absorbed, but normally taken out as a solid because it's cooled down so much. And then you're left with some liquefied remnants of the air, and out of the little bit like fractional distillation of crude oil, out of that you'll get liquid oxygen out of the bottom and gaseous nitrogen out of the top. The oxygen here sometimes comes out with argon because they have similar boiling points, both in the minus 180s. One's minus 183 and one's minus 186. So similar melting points and boiling points, and that's why they come out at the bottom together. So moving on to the next summary, we'll look at extracting metals. So there's several different ways you can extract metals, obviously really useful for loads of different building purposes. We'll look at reduction, displacement, electrolysis, phytomining and bioleaching. So first of all, see if you can recognise what type of reaction this one is here. So you've got iron oxide plus carbon turning into iron plus carbon dioxide. Think about what's happening. Well done if you said that that was a reduction reaction, called reduction because you're removing the oxygen from the iron, leaving iron and carbon dioxide. So really useful if things are below carbon in the reactivity series, you can use reduction. So this one will often happen in a blast furnace. You get quite impure iron out of it, which is a bit of a problem. It can be quite brittle. You'll also hear the word smelting or the process smelting surrounding this, which is heating the ore up to a really high temperature, and then the reduction reaction will help in the smelting process to remove the iron. This reaction here, have a look at it, copper sulfate and iron, making iron sulfate and copper. So in this reaction, you're wanting to extract copper. Have a think about what type of reaction that is. Well done if you said displacement reaction, because the iron is more reactive than the copper, so that will come in and displace the copper, leaving you with iron sulfate and copper. So why this is good is because you can use scrap iron for the process, which brings the cost down, makes everything a little bit cheaper. Trouble is, with the copper, it's got so many uses, wires, electrical wires, piping, but the trouble is high-grade ores are running out. Okay, so that means ores with a high percentage of copper in. If you remember, an ore is a rock containing enough metal for it to be economically viable to extract. That means your rock has got to have enough copper in it for you to make money by putting lots of energy in to extract that copper. Now, these ores with lots of copper in, these high-grade ores, are running out. So there's a few new technologies, first one involving plants and the other one involving bacteria. See if you can name them. This one is phytomining, and the one involving bacteria is called bioleaching. The reason these are needed is because these high-grade ores are running out. We can grow plants or a culture of bacteria on low-grade ores and then extract the copper. The plants will absorb the copper compounds, they can be burnt, and then in the ashes you'd have copper. You could then add maybe sulfuric acid to make copper sulfate, and then perhaps do electrolysis by putting that blue liquid in here to get your copper out. Obviously it's not magnetic, you can't just put a magnet in the ash and get that out. So there is a slight other separation process needed for that one. Electrolysis then, yes, it requires a lot of energy, they like that, it makes it expensive. So all the E's for electrolysis, expensive, energy, but you need it for certain metals like aluminium. Anything above carbon in the reactivity series, you can't use reduction or you wouldn't use displacement, so you have to use electrolysis. Again, remembering that the ions are on your periodic table, so if you have something like this, you can work out that that is the positive one going to here, that is the negative one going to here. I'm not going to dwell on the detail of electrolysis because that comes up in a lot of C2 and I'm sure you've revised it a lot, but bear in mind that you do get the purification of copper as well. So if you've got an impure piece of copper and a pure piece of copper, you need to think about which electrodes they need to go on, because you want this one here to be the negative electrode, so the copper ions move across, and this to be the positive one. This will lower in mass and this one will increase in mass, and you'll end up with impurities or sludge at the bottom. So those are all the different ways that metals can be extracted. Just a question whilst we're here, just on this first reaction, whether it can be called displacement as well. Technically, oxidation and reduction can look very similar to displacement sometimes, but because it's the removal of oxygen, it has to be reduction and not displacement. Displacement is when you've got two metals often that have a different reactivity, that they are kicking each other out, and this one is very definitely the removal of oxygen. So make sure you're talking about this one in terms of reduction and not displacement. Okay, next little bit then, we're going to talk about metals and alloys. We just talked about getting metals out. Well, let's talk about a few special metals. First of all, this middle block here, which hopefully you'll be able to name as the transition metals. As you go on to C2 and C3, you talk about these a lot more, but these are talked about a little bit in the topic as well, as being strong, you know, the properties of them, strong, high melting point, high boiling point, etc. Alloys we'll talk about. These come up in C1 and C2. You need to recognise this diagram here as being a pure metal, and these tend to be soft. So you've got metal atoms in layers and they slide easily. So if we're talking about describing this for 2 marks, we need those 2 points. The metal atoms are in layers, or you can say metal ions, and the layers slide easily. This second image here you need to recognise as an alloy, and describing it as different sized atoms, and the layers are distorted and can't slide easily. So this makes the alloy harder. That's why you might want to take a soft pure metal, something like pure iron, and this could be iron, sorry, this could be carbon and iron to make steel. Okay, you don't want necessarily pure iron. It's very soft, it's not got as many uses. If you want a harder, stronger material, then you would mix iron with another element. Could be a mixture of metals. You get a mark if they said what is an alloy, and if you put mixture of metals, you'll get the mark. But in the case of steel, it's a mixture of a metal, iron with carbon. There are different examples of steel that you can have. So as I said before, the iron that comes out of a blast furnace is a bit brittle. Okay, so it's about 96% iron. It's a little bit brittle. There's a lot of problem with bridges in this country that are made out of cast iron because they're starting to show their fragility a little bit. So they want those impurities out, so things like sulfur and etc. that they'll want to make pure iron, like this one up here, without impurities in, but then they can add the carbon to make different steels. And there's 3 different steels that you need to know about. There's low carbon steel, which is about 0.01% carbon, just a little bit of carbon in there. Still quite soft. Okay, you can make that into shape that into car bodies and things like that. So if you remember, if it's just a little bit of carbon in, it's still quite soft like this one. If you add more carbon to make a high carbon steel, that's got about 1.5% carbon in. The layers are going to be distorted a lot more. It's going to become a harder material, and they tend to be used for things like drill ends or tools and things like that. And finally, stainless steel, bit of chromium in there as well, and that can be used for cutlery and things that you don't want to get stained and tarnished. 2 metals that we need to know about in a little bit more detail are aluminium and titanium. Now, see if you can think about which material, aluminium or titanium, is often used in airplanes or hip joints, and the reasons why. Well, they both have very similar properties. It is, well done if you said it, aluminium that is often used in aeroplanes. Obviously, often an alloy of aluminium, but quite a big component of aluminium. And the reason that's most useful in aeroplanes is because it's at low density, so it's quite light. It can get up in the air, but also importantly, it is resistant to corrosion. And the same properties, low density and resistant corrosion, also make titanium a useful metal in hip joints. Okay, because the titanium inside your body, if you just had a new hip joint, you don't want that to be a heavy, dense metal, so you want it to have quite a low density. And obviously, you don't want that reacting with your body, so you want that to be resistant to corrosion as well. I'll stress whether it's C1 or C2 that this question is so common. So if it's not in your C1 exam, I kind of expect it to come up in your C2 exam, this kind of shape of pure metals versus alloys. Next section then, quite a big section. We're going to go all the way from oils to plastics. So for those of you who just joined us, you can start on this section, and you can always go back and watch the start of the Hangout a bit later on. Fractional distillation then. What goes in is crude oil, a mixture of hydrocarbons, so of different lengths, short ones, long ones, and they all need to be separated because whilst they're all a mixture, they are not useful. But if we put it into the fractional distillation tower, heat it up, we can separate them. Just think about, how are they separated? They are separated because they have different boiling points. Remember, boiling points is the same as condensing point, depending on whether you're cooling something up or heating it. Sorry, cooling something down or heating it. So if something has a boiling point of 216 degrees C, it also has a condensing point of 216 degrees C. So while crude oil gets heated up, have a think then, which fractions come out the top of the tower and what properties do they have, and which fractions come out the bottom of the tower and what properties would they have? So well done if you remember that the short fractions come out at the top of the tower. They are flammable, really useful fuels, that they are volatile, and that they are the short hydrocarbons. And down at the bottom, they are the long hydrocarbons, so often bitumen, used on roads, really long, thick, gloopy. They are viscous, so thick and gloopy, and they are the least flammable and the least volatile. Volatile meaning turns into a gas easily. So you don't need to know the order or the names the fractions come out, but just be aware, because they may talk about it. Petrol is higher up of the fractional distillation tower than diesel. So if we talk about cracking a little bit later on, if you really, really have a high demand of petrol and there's not enough, but you've got loads of diesel, then you could crack these long chains of diesel to make the petrol. Let's talk alkanes and alkenes then. The majority of these molecules that are coming out of here are alkanes. They are saturated. That means they have all single bonds. No more hydrogen can fit round. It's full of hydrogen all the way around and all single bonds. Really, all you need to be able to draw is methane, ethane, propane, butane. Monkeys eat peanut butter. So that is one carbon. So methane would just be like this, all the way down to butane, which is this molecule here. 4 carbons full of hydrogens all around the outside. This molecule here is an alkene. Because it has a double bond, it is unsaturated. Don't forget, all of these lines here represent single covalent bonds, okay? The alkene is unsaturated because it's not full up of hydrogen. You could add more hydrogen. The test for an unsaturated molecule, often we talk about this in terms of vegetable oils instead of fuels, but that is bromine water. Goes from orange to colourless. Don't say clear, it must be colourless. So useful both for fuels. Alkanes and alkenes. Alkenes can be made into alcohols, for example, ethanol, methanol, and these alkanes can be used straight away as well. How do we get them from an alkane to an alkene? Well, you'll have a long chain alkane. I'll just about fit that hydrogen in there. There should be a hydrogen on the end. You have a long chain alkane. I'll not draw the hydrogens on, but you get the idea. That you might want to crack, and if you do so, you would use heat and a catalyst. You don't need to know the specific name of the catalyst, although it's often something from a transition metal like aluminium oxide or something like that. Sometimes just a piece of simply pottery or clay as well as the catalyst. That can be broken up then into alkanes and an alkene. So it could be several different products. You could just have 2 products, or it could be several different ones. Let's assume then that this became the alkene. So, sorry, I'll draw the alkene over there. This could be the alkene. So you'd have 3 carbons with a double bond. Remembering each carbon can only make 4 bonds. So that could be our product. Let's just check. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4. That's our check. So that could be one of our products of cracking. And assuming it only makes 2 products in this case, our second product would be a 4-carbon alkane. So they might ask you to crack a long molecule like that. They might give you a molecule with maybe 8 or 10 carbons in that you need to crack. And don't worry about having a right or wrong answer. It can literally crack anywhere, and you could have a number of different products that you make. So going on to how we then take an alkene and we make that into a polymer. So the whole point of going from all the way from oils to plastics is that every bit of plastic, pretty much, that you use in your day-to-day life originates from crude oil. Crude oil is separated, You get your long chain alkenes, they're cracked to make alkenes, long chain alkanes, sorry, cracked to make alkenes, and you can turn these into a polymer. So this here, this image here, is a polymer subunit. What you're doing is essentially taking an alkene, which I'll just represent as a circle, and under the polymerization process, you are joining that up to loads of other alkenes to make a polymer. Let's take this example. The monomer unit for this, which is a single unit, is ethene. You often put an N here and an N here on these. So this is the monomer unit. This is just saying that one of these is ethene. And if we join loads of them up, you make this polymer subunit. So imagine those brackets in here. You're just saying that section of the polymer I'm going to represent down here. So that's the monomer unit, all joined together. You represent it like this is a polymer. Oh, just notice that one actually. This is not ethene because I've put 3 carbons in. You need to look out for that. So this one here, just look carefully. 1, 2, 3 carbons. So that is propene. So you'd have the CH3 there. Apologies for that. But you need to look out for that one. They might say name the polymer. So just count the carbons up. Sometimes some of them are hidden down here. A lot of people only look for those 2. So this monomer unit would be propene. And to name the polymer, you just put the word poly in front of it. So this polymer would be called polypropene. Just like if you had styrene, the polymer would be polystyrene. If you had butene, the polymer would be polybutene. So the conditions then we went through before for polymerization, because you're squashing things together, you need a high pressure and a catalyst. The question before about whether you have to name the catalyst, it's very rare that you do have to name the catalysts involved in the reactions, apart from the nickel catalyst in hydrogenation. But just have a look in your revision guide. Occasionally they gave you an example. You can just have a look through at what catalyst it is, but I'd very much doubt that they ask you for a specific catalyst. So once we've got that polymer, then just bear in mind that the conditions under this process can make different types of polymers. So if you change the temperature or the pressure conditions, when you make the polymer plastics, you can make them with different properties. So depending on what the manufacturer wants to make, they'll change the conditions at the time of polymerization. Okay, next topic then. We've just got a couple more to go. The next one is limestone cycle. So we start off with calcium carbonate, which you need to know is CaCO3. If you heat that, hopefully from before you'll remember what type of reaction that is. It's a thermal decomposition reaction. And you release carbon dioxide and you end up with calcium oxide. Add a little bit of water, you end up with calcium hydroxide, and then add a little bit more, you end up with aqueous calcium hydroxide, aka lime water. Remember, if you add carbon dioxide to lime water, it will go cloudy. And the reason it goes cloudy, if they say things like, what will you observe? Well, you'll observe calcium carbonate precipitate forming. I'll just mention that again because they might see in the exam, what do you see happening in the reaction? What do you observe? Well, if you've got lime water, you're adding carbon dioxide. First of all, you'll see bubbles of carbon dioxide going in, and then it will go cloudy because you'll have a calcium carbonate precipitate made, hence the solid. Calcium hydroxide, think about what pH that has and what that is used for. Well done if you said that is alkaline, and that is used by farmers to neutralize acidic soils. Limestone then, really useful, makes really nice buildings, nice to look at, but also it makes other useful products. It makes cement. That is a mixture of limestone and clay. A couple of facts that people tend to forget to revise. Mortar, which is the stuff in between in the bricks. If you Run your hand in between the bricks, you'll feel a sandy texture. That is because mortar is made out of limestone, clay, and sand. And finally, even tougher than that is concrete, and that's because you've got all of the above plus aggregate, which is like small gravelly stones as well. So useful product is limestone, creating cement, mortar and concrete, as well as obviously going directly to make buildings. That's a building, by the way, as well. So next two, we've only got two more to go. You'll be pleased to hear, and then you can go away and have a look at your last minute things for getting a good night's sleep ready for tomorrow. Environmental problems then, they love this idea. Always look out for an exam, any situation where you might get some form of sulfur reacting with oxygen, maybe as part of a big flow diagram. Sometimes you've got, when you're talking about extraction of metals, they'll randomly have a really big flow diagram, loads of information, and sneakily in there they'll have this idea. Because they love you to make the link between sulfur reacting with oxygen to make sulfur dioxide, and that leading to acid rain. Same for carbon. If you ever see carbon and oxygen coming together, think carbon dioxide, and that links to global warming. Solid particulates then, caused by incomplete combustion, so that soot is carbon, but that causes global dimming. Not a massive problem in this country, but if you go further east, then big industrial countries like China have massive problems with global dimming because of the amount of solid particulates. They really like mentioning and emphasizing saving the planet, so recycling, reusing, reducing, to conserve energy, to conserve resources, so whether that's fossil fuel or whatever it is. And they also like the idea of reducing the amount of landfill we've got. At this point, I'll just remind you that plastics are a massive problem in landfill because they don't biodegrade. Have a think about whether you know what we put into some plastics so that they become biodegradable. There's a new kind of polymer that we can make. Well, I don't know if you remember that that's adding cornstarch to make a biodegradable plastic, because the little microorganisms can break down the cornstarch, and that allows the plastic to at least break down into little pieces. So most of it isn't a big problem with people chucking away plastic bags and things like that, so we need to reuse, recycle and reduce as much as we can. They like mining, quarrying, very similar things. Mining tends to be associated with a small little pothole that you make where all the men or women walk down and get themselves very dirty, trying to get coal or whatever it is out of there, or their metal ore. Very similar to quarrying. Quarrying tends to be slightly different in the fact that it's a massive hole in the ground. So just like this picture over here, a really big quarry, looks like a limestone quarry where they've literally dug a massive hole in the ground. Obviously, both of them have environmental problems. So some downsides to this is that they create a lot of noise, dust, a scar on the landscape or an eyesore, destruction of animal habitats. Few pluses though. They make useful, or they allow us to have useful resources. For example, limestone, really useful for building, etc. They provide some local jobs as well. Final topic then is oils and emulsions. So very well done if you stuck with me, and hopefully this is useful still. So oils and emulsions, extracting vegetable oils, looking at unsaturated versus saturated oils and emulsions and things like that. First of all, really kind of old school style extracting oil is by having your plant material, like olives, for example. A lot of you would have heard of olive oil. Well, that obviously comes from the olive plant. It needs to be crushed, first of all, and then pressed. For example, these are millstones, really, but between two really heavy stones, and you'll have the oil dripping out of the side. Then it needs to be often spun round in a circle so that the oil all drips out into a container, but still then it is often impure. Naturally, you're going to have little bits of the olive branch and things like that in there, so you might need to use this process. Have a think about if you know what this process here is called. Well done if you said distillation. So a separation process involving evaporating and condensing. Here you'd have your oil and your water from the plant and other plant bits in here. The oil and the water would have different boiling points, so you'd heat it up until the oil evaporated. That would then condense down this condenser, and then you'd end up with your oil in here. So a few places involved with actually extracting that oil first of all, but once you have it, really useful oils. So there's two different types, unsaturated and saturated, just like with the fuels that we were talking about earlier, with the number of hydrogens on them. If you want to get from an unsaturated oil to a saturated oil, hopefully you'll remember the process of hydrogenation, which is adding hydrogen. And the conditions needed for that, if you remember, are a nickel catalyst and 60 degrees C. Unsaturated oils are a lot healthier than saturated oils. These are quite unhealthy, can lead to cholesterol buildup in your body. The hydrogenation process turns the oil tends to be a solid at room temperature when you've saturated it, but the unsaturated ones tend to be a liquid. They're a lot healthier. Again, test for unsaturated oils using the bromine water, which goes from orange to colourless if they find that carbon-carbon double bond in there. They will ask about why these are better to cook in, so advantages like they'll cook quicker, they taste nicer, they make food crispier, they make food a better colour, that kind of thing. Finally then, emulsions. Examples of emulsions, including things like paint, ice cream, moisturisers. Advantages then, they give a better coating of things, better texture. This example is when you've got oil as your droplet and water around the outside, and this is the opposite example of where you've got a water droplet here and oil around the outside. Can you remember the name of the molecule that allows an emulsion? Well done if you remember. It looks a little bit like this, and it's called an emulsifier. So normally oil and water don't mix. If you had a beaker of water and oil, you'd have a layer of oil at the top and your water underneath. Normally they don't mix, but if they do, they can make things with better coatings, better textures, etc. So you can use this emulsifier molecule and it will help bind the water and the oil together. It has two ends. This one is called, well, I remember it as Phil. This is Phil. He's hydrophilic. He loves water, okay? Hydro in relation to water, philic, loves water, but the tail is hydrophobic, doesn't like water. Hence, you'll have these two different situations. Here, the tails are in the oil because they are hydrophobic, they don't like the water, but the heads are in the water side because they are hydrophilic. Opposite way around here, this is the water molecule, so you've got the heads on the inside because they like the water, and then the tails sticking out into the oil. So that allows the oil and the water to mix. So One more final thing with the saturated oils that I just remembered. Sometimes you'll see in the exam mono unsaturated. Okay, that is one unsaturated oil containing one double carbon-carbon bond, and poly unsaturated would be an oil that contains more than one double carbon-carbon bond. So it might be a long molecule where they have several double carbon-carbon bonds in them. Probably won't come up, but they will perhaps refer to those names: mono unsaturated and poly unsaturated. Okay, well, very well done for following through the whole of the C1 course. That brings the Hangout to an end. Feel free, once I've come off, to go back and look through any other bits that you weren't sure. I will hang on for another 5 minutes until 7 o'clock, just to catch up on any questions that you have asked. And also, if there's anything further that you want to ask, feel free to do so on the Frog page. I'll take this point to say, relax. Okay, you would have done a lot of revision already. Hopefully, I've just gone through an overview and everything, and you'll come away pretty confident with what you've heard this evening, and nothing's a big surprise to you. When it comes to the exam tomorrow, take your time, use your highlighter, and make sure you have a good night's sleep and get a good breakfast in the morning, ready to do the best job that you can. So I'll sign off for the evening. I'll just wait for any more questions, but for now, have a good evening. Okay, I've just got a question about bioleaching, which we'll come to in a minute. We'll just go through bioleaching first of all. So if we go back to that. Okay, luckily with bioleaching, there's not actually a lot that you need to know. You don't need to go in very much detail at all. Let's take it over here just to help you explain it in a bit more detail. Again, you'd have a low-grade ore that you would grow a culture of bacteria on. So let's just show it like this. Okay, massive cultures, really cheap way, growing loads of bacteria on there. The bacteria benefit because they gain energy when they break a bond within the copper compound. So this is often something like copper sulfide, for example. And you'll want the copper out of that copper sulfide, so the bacteria will break down that bond. Okay, and in doing so, they'll gain energy, but also you'll get their copper separating from the copper sulfide. And what you'll get is the bacteria then creating a solution called leachate. And all you need to know is then you can extract the copper from the leachate. So not as much detail as you need to know for phytomining. Just know that bioleaching is to do with bacteria growing on a low-grade copper ore and producing a leachate, which is like a solution containing the copper, which you can then extract it from. Okay, just going back to the metals very quickly, a question on the differences between aluminium and titanium. They have very similar properties in that they have low density and are resistant to corrosion. Those are the properties that make them really useful. But this one is just less strong compared with aluminium. So two completely different metals. Aluminium found over here on the periodic table, completely different to titanium. Very similar properties in the fact that they are both low density and resistant to corrosion. However, titanium is just less strong than the other ones. Okay, just a couple more questions to get through. Okay, question on whether you need to know the specific catalyst for polymerization. I've never ever seen a question on that in an exam. I very much doubt that you'll be asked that. There's no mention of a specific one in your specification, so they will ask you about the specific one for hydrogenation, but fingers crossed not for polymerization, because you can have different catalysts for different polymers. Just like you can change the conditions of polymerization to make different polymers, you can have different catalysts and different temperatures and things as well. A question about why unsaturated oils are healthier. Not sure into the details of why. You won't be asked why they're actually healthier, but you will need to know that they are compared to the saturated ones, the ones that are solid at room temperature. But it will be all to do with how they're broken down in the body and how the body stores those lipids that come into the body. So not sure entirely about why they are, but just be happy that they are the ones with the double bond in, less hydrogen, and that they are healthier than the other ones. Okay, question just come in about whether you'll get asked about the periodic table and all the names of the groups and how reactive each group is in that. That tends to come up in a little bit into C2 and more into C3, especially. They won't ask you about the reactivity of halogens or alkali metals or anything like that. That will come up in C3. They tend just to ask where the transition metals are, where the noble gases are, knowing that those are in group 0. They'll ask specific questions about electron structure and the number of protons, neutrons, and electrons and things like that. But they don't go, oh, and you need to know that the group number tells you how many electrons there are in the outer shell, but they won't go into detail about asking you about the development of the periodic table or any details really about reactivity. Okay, I think that is all questions answered. If you do need anything further, then feel free to pop up and see me tomorrow. If not, make sure you get an early night, look at any last little bits, and then leave it. You've done as much as you can so far. So good luck in your exam tomorrow.